Okay, so we were looking at inequality constraints. So the problem is now to minimize or maximize a functional. So the problem formulation is like this. I have F5 from, yeah, we are trying to minimize F naught of X under the constraints F1 is less than or equal to 0, etc. up to Fn less than or equal to 0. This is a typical optimization problem with the inequality constraints. Now we saw that if all the FIs are linear or affine, its linear programming problem is very much studied by different algorithms are available. I was looking at the other case, general function. In particular, if it's a convex function, we can say much more things. So define the Lagrange function Lx lambda. So you see it's Lx lambda here I have written I is equal to 1 to m. I think that is why they asked Lx lambda should have lambda naught f naught to m. So it should be, let me, now I understand the question. I should be from 0 to m. So lambda naught f naught must also be there. I have written wrongly here. And the Lagrange multipliers lambda I are all non-zero Lagrange multipliers that we will assume. Lambda naught is always assumed to be greater than or equal to 0. Now I assume all the FIs are differentiable at x naught. Then what is the KKT condition? At a point, first of all, stationary condition tells something like earlier that gradient of L at x will vanish, at x naught will vanish, and all the lambda i's will become non-negative, the 1 to m. Already I had assumed lambda naught was non-negative, so now it is others are also non, they can be 0. In fact, the third condition, complementarity condition, says either lambda I is 0 or fi is 0. So I have m of them, these conditions. So how do we use it to solve a problem? So let us take a very simple baby example. So we want to find the point closest to 2, 3 under the constraints, the sum of the coordinates. So I am in R2. Okay, so the problem is posed in R2. I have to find x1, x2, which is very closest, the nearest to 2, 3. But there are also constraints. The sum of the coordinates not larger than 2. That means x1 plus x2 should always be less than or equal to 2. And the first coordinate not larger than 2 in absolute value, or which means modulus of x1 is less than or equal to 2. So I have written the Lagrange function lambda naught. The function will be, the f naught is the minimize the distance from x1, x2 to 2, 3. So x1 minus 2 square plus x2 minus 3 square. So that is the f naught. Now, what are the constraints? The first constraint is x1 plus x2 is always less than or equal to 2. So that the f1, the constraint function is x1 plus x2 minus 2. So that is equal to less than or equal to 0 is the first constraint. I multiply it by the Lagrange multiplier lambda 1. The second constraint is modulus of x less than or equal to 2. I have rewritten it as x1 square minus 2 because modulus is differentiability problem. This is a better way to write. So lambda 2 times x1 square minus 2. Okay, so I have my function. So remember this, we go to the application of KKT. Now, what does KKT give you? So I need to keep the function in sight. So this is my function. So the KKT, when you apply, the first one is dl by dx1 must be 0. So when I differentiate, I'll get, so I have taken lambda 1 is 1. That is, sorry, lambda naught is equal to 1. So the first one is, this is 1. So this will give me 2 times x1 minus 2 from the first f naught function. From the f1 function, I'll get lambda 1 because it's a linear factor. From the F2 function, I'll get 2 lambda 2 x1 is equal to 0. So I have one equation. Now you differentiate the same L with respect to x2. So again, lambda naught is 1. So I'll get 2 times x2 minus 3 and lambda 1 into 1. And that's all. So the second equation will be 2 into x2 minus 3 plus lambda 1 is 0. Now the second condition, non-negativity, says lambda 1, lambda 2 can only be non-negative. They cannot be a negative number. And the complementarity condition tells the product of lambda 1 with the constraint F1 must vanish. And lambda 2 and the constraint F2 must vanish. So either lambda 1 is 0, the other one is not 0, lambda 2 is etc. etc. So as you can imagine, there are many possibilities. Okay. So what I tried to do is I first assume both lambda 1, lambda 2 equal to 0. Then what happens? Can I ask you to check if the participants have a pen and paper? It will be easier if you also try, instead of me showing the slide. I see there are some questions. Anything urgent, Abhay?
So not urgent, but related to this only. Can I
Okay.
read that?
Yeah, please read. When they are
Uh,
checking what happens when lambda 1 and lambda 2 both are 0, does it lead to a solution? That's what I want to know. Solution in the sense acceptable solution. It should satisfy the two constraints and it should be a point closest to 2, 3. Yeah, okay, go ahead, Abhay.
so the first was, Madam, I think there will only F0 not multiplied with lambda 0 because it is our cost function and Lagrange multipliers are there with constraint function.
Yeah, he is right. But as I told you, there are some degenerate cases. So convention is to take a lambda naught to avoid the degenerate cases. And mine is example is not a degenerate one. So I have put lambda naught is 1. See, he is right. If he wants, he can take out the lambda naught. That doesn't matter. It doesn't
Yeah.
affect anything. Yeah, next.
Okay. The next one is it should be 2 or 4 in Lagrange function third term. I think earlier slide.
Earlier slide. This one? This is the theorem with the M.
Yeah,
So
no,
in the example you are saying?
In the third term, whether
in
it
the
should be
third
2
term.
or 4 in the constant. In the third term on the right hand side.
So 4. Yeah, he's right. He's right. Mod x1 he's right. I made a mistake. Should go to 4. I have written 2. Yeah. Thank you. That was a mistake. X1 is less than or equal to 2 should translate to x1 square minus 4. I hope my equations are correct. That doesn't appear in the equation, luckily. Yeah, the equations, they don't appear, so it's okay. Here it will be 4. Correct? Yeah. Okay.
So other questions were related to this only, x1 square minus 4
X1
also.
square less than or equal to 4. I made a mistake. Yeah, thank you. So let me go to the solution. Probably you tried. What happened if lambda 1, lambda 2 are 0? So this will vanish. I have only one possibility. X1 is 2, X2 is 3. And obviously it will not be a solution. Why? Two comma 3, can it be a solution at all? Does it satisfy the constraint? Because x1 plus x2 must be less than or equal to 2. X1 plus x2 will be 2 plus 3 will be 5. That is not less than or equal. And also it's it doesn't satisfy, the second in the condition is satisfied, but the first is violated. So I see the first, if I call it constraints being tight. That means that constraint is strictly less than 0, which means lambda 1 must be 0. F2 is strictly less than 0, which will imply lambda 2 is 0. Then I have this possibility, which is clearly not a solution. So I took up the next one. Lambda 1 is 0. Then again, what happened? I hope this calculation goes through. When lambda 1 is 0, this goes, but this goes. So I get x2 is 3, but I'll have a lambda 2 hanging. So I'll have to solve for x1 and lambda 2. I have done that, I suppose. So x2 is 3. x1 square, luckily here I have done correctly. x1 square minus 4 is 0. And the next equation is 2 into x1 minus 2 plus 2 lambda 2 x1 is 0. This will lead to x2 is 3, but again x1 will come to 2, which is again not acceptable because the sum of the coordinates will be 2 plus 3 will be 5. That is not an acceptable solution. So let us go to the next possibility, which is lambda 2 is 0. Then when lambda 2 is 0, this term won't be there. When lambda 2 is 0, this is not there. I will have 2 into x1 minus 2 plus lambda 1 is 0 and the next. So what I could do is I can try adding them up because x1 plus x2 we know. x1 plus x2 minus 2, I know something, so I could use that. So what I did, I think I tried to solve for lambda 1. That gave me 3. Lambda 1 happened to be 3, and then x1 was half, x2 was 3 by 2. This is an acceptable solution because x1 plus x2 is 2, which is admissible. And modulus of x1 is strictly less than 2, which is also acceptable. So this is the possibility. Lambda 2 is 0. Lambda 1 is different from 0, but it's positive. And then I get the point. So you see, even in the case of 2 variables and just 2 constraints, we have to eliminate so many cases. And you keep eliminating, and then if you have m number of constraints, it quickly goes up to 2 power m and it becomes impossible to do it by hand. So by convexity of the objective functional f naught, this is the unique minimum, so I can stop. But there is a very easy geometrical way why we had to. So what the problem was, yeah. So here, if you look at the, so let's say this is 1, 2, 3, and this is 1, 2, and 3. So my coordinate was 2, 3. So this was my point 2, 3. And the first condition says sum of the coordinates not larger than 2. That means I have to look at x1 plus x2 equal to 2 will be this line. This will correspond to this x1 plus x2 equal to 2. So this should be the region where I should look for the point. And first coordinate not larger than 2 means the first coordinate can only lie below this. So this is the region. And here you can easily obtain by projection, because this is a convex set, you can drop the normal and you can find out geometrically more easily, verify that your answer is correct. But I did this only to show that KKT conditions lead to lot of possibilities. You have to eliminate one by one. Even in the simple case, it takes a long time. So let me stop here.
Madam,
Yeah.
there is one question. Kindly explain about convexity. And there is another one, I don't know which slide he's talking about. Why you take lambda 0 to be 0? Is there any research? I
No, I
guess
did take lambda 0 to be 0, lambda 0 to be 1. If lambda 0 is 0, I'm sunk. I lose my functional F naught. So I don't want that. So I had the only condition is sometimes gradient of f or gradient of g is degenerate. At that time, I may require some such thing. Otherwise, we don't need. Those are very pathological situations. So forget about lambda 0. Lambda 0 is always 1 for me. You forget about lambda 0. Okay. Yeah. But traditionally, in most of the standard finite dimensional optimization books, they start with lambda 0. So I followed that procedure. That's all. Okay, so now I'm at the end of this lecture.
There was
Yeah,
another one. Kindly
yeah.
explain about convexity. That's what.
Oh, convexity. Yeah, convexity. I had a slide, very short thing about convexity, no? Yeah. Yeah, this how to motivate this condition. So suppose I have, okay, so let me draw a function. So this is, so this function, if I try to say, this is the point x comma fx. So what I wanted to say was the epigraph is the points above the graph of this function, that will be a convex set. And the secant, if I draw a secant from point joining A and B, this secant will lie above the graph of the function. That is this condition analytically explained. Geometrically, it means any secant lies above the graph of the function. So that is what it means for every k. So the k is between 0 to 1. Now the convexity has several interesting properties. So this is a convex function. So it satisfies this property. So it becomes continuous on open set, and its derivative will have certain monotone property. And second order derivative, you can say, and that is why the first order necessary conditions become sufficient. And local minimum becomes global, etc. And if you are strictly convex, what is strict convexity? This inequality becomes strict inequality. Then you will get only one minimum. Then you don't have to worry about anything. Okay. So that is what, let the references, I was showing the references. Let me go back to the references.
There is another question just now.
Yeah. Tell me.
What do you mean by degeneracy here? I think while explaining the convexity.
The gradient G can be 0. So I don't want such abnormal situations. So we don't have to, I'm not teaching geometry here since I didn't want to go into that. So I don't want to go deep into that. Can we stop here and go into the next lecture? If there are questions, I'll take it up later.
There is one more. I think you have answered
Okay.
it, but let me read it.
Yeah,
What
please go ahead.
happen if you don't take lambda 0 not equal to 1?
I'll get a variable, suppose I take it to be 2, what happens? Or I take it to be 1.9, what happens? So I'll get a constant, but the answer will not change. We can verify that because it's independent of, all I need is x1, x2. These lambdas were all some instrument to arrive at my optimal point, x1, x2. Right? So they are not playing any role. I'm not interested in the values of lambda, but I'm interested in the solution x1, x2. So it only is an aid to calculate the optimal point. So it doesn't matter what I take lambda naught. So without loss of generality, I will take the simple number 1. Okay. Yeah. Okay. So
There is
yeah.
sorry, there is another one.
Okay.
Shall we take it?
Yeah, please take
Uh,
it.
uh, can we say all the continuous and differentiable functions are convex?
No, absolutely
So,
not. There are concave functions, of course, and there are such functions which are neither concave nor convex. So there can be all kinds of crazy functions, right? Like sine 1 by x, which goes on oscillating so many times. So yeah, so convex functions are very special privileged class, but they are very useful. That's all I can say. And if the function is convex, we are able to solve some of the optimization problem better. So the progress has been there more in the convex optimization problems. There are also some work on non-convex optimization, but I'm not very familiar with that, so I don't want to talk about it. Okay. Yeah. Anything else?
oh, that is all as of.
Okay.
This lecture notes by Ivan's, who is the publisher?
No, it is not published. I found it in his web page. Evans puts all his lecture notes in his web page, and I have, I mean, it's freely available to everyone who goes to his web page, and I find them extremely useful. He has a whole series of lecture notes, something on finite dimensional optimization as well as optimal control and calculus of variations. Everything he has a series of lecture notes. I have referred many from some examples from his, many examples from the first one, Brinkquist and Tikmirov. That is a very nice, easily followable Princeton University Press book, which I will suggest. Of course, they don't go very deep into the other topics, but for finite dimensional optimization, wonderful examples, a lot of practical examples are there. And Donald Kirk is more of optimal control, but he has initial chapter on finite dimensional. And Tikhomirov talks a lot about the history, maxima, minima. This was a beautiful, most of my historical things I had borrowed from Tikhomirov. Okay, so this is time. Yeah, anything else? The second lecture, I wanted to take up calculus of variations and optimal control. So whatever is possible, let us, let me remove all this. Okay. So I organized it like this, a little bit of history, and then I'll start with calculus of variations, and then we will go to optimal control. There are two broad approaches, one by the Russian school using Pontryagin maximum principle, and one by the American school, Bellman, via Hamilton-Jacobi-Bellman equations. So I'll try to give some things, but examples, I won't have many to have time to do all this. Okay, so how did this problem come about? It was Johann Bernoulli. Of course, I should say probably Galileo was the first. In his notes, he has some pictures of brachistochrone problem, but he couldn't solve it. I think Johann Bernoulli, who was in 1667 to 1748, late 17th century, he started looking at this problem. And he solved it in 1696. And so what was the problem? Let me explain. Find the path taken by a bead falling freely under gravity from point A down to point B. Let's say they are all in vertical plane, in the same plane, and there is no friction. It is just falling under gravity freely. And it should fall in shortest time. So this was also bothering Galileo. He wanted to know how. You may remember he had many experiments, feather and stone, which will fall fast. So he was always interested in such questions. And the answer Bernoulli found out was cycloid. And the path traced, what is cycloid? It's the path traced by a point on the circle when the circle rolls along a straight line. So that is the curve which he found as the answer. Then he published a note, a new problem that mathematicians are invited to solve. And in fact, there were many who attempted, including Newton himself, and some more, I forget the names. And one important one was Johann Bernoulli's brother, Jacob Bernoulli. Actually, the story seems like the brother had a correct proof, whereas this man had a wrong proof. But anyway, this was solved by each one gave very different solutions, and each procedure became one mathematical area very soon. And then he later asked his student Euler, 1707, 1783, that was almost 18th century, Euler took it up. And so the problem he gave to Euler was generalize this to all such problems. And Euler did solve this. He found a general method. And that is what he called calculus of variations. And meanwhile, Lagrange also found this. He, in 1959, he wrote to Euler about his method of variations for these problems. So Euler responded that he too has a solution which he called calculus of variations. Both of them more or less, so they came to the same conclusion. So the first order necessary conditions are now known as Euler-Lagrange equations. So that then came about calculus of variations. And a little later, around not little later, quite 2 centuries after. So around 1950, Pontryagin in Russia started seminars on mathematical theory of control. This was the wartime, and there were many such problems coming up. And many leading scientists were invited to present concrete problems that they encountered in practice. So Pontryagin school formulated this class of problems as optimal control problems. And they are very close to calculus of variation problems. Then here the necessary conditions for optimality, they came to be known as Pontryagin maximum principle. Meanwhile, in the US, Richard Bellman also had arrived at such optimal control problems, but in a different route. He called it dynamic programming principle. So I tried to indicate a little bit of these two. So as you can imagine, all these are happening in infinite dimensions. So we have to worry about functional analytic setup. So my space X is C1 functions on the real interval 0a, let us say. And this has a vector space structure, and I can even define a norm on this space X. So it's maximum of modulus of fx plus maximum of modulus of f prime x. So this I can give a norm to this work, this space. And so this is a nice normed linear space, and it has all good structures. It's then I can even define differentiation as linearization. That is where Fréchet defined, some people call it Fréchet derivative. That is how he arrived at the definition. And so once you had the notion of derivative, a lot of tools were developed, all functional analytic tools were developed, and Fréchet and Ries, this is the early 20th century, there was a strong development of activities in this direction. Calculus in non-linear spaces, Banach space, Hilbert space. And so in this case, then we can again write down Fermat's rule for optimization. What is the Fermat's basic rule? The derivative should vanish. So that will be the basic Euler-Lagrange equation. So calculus of variations gives the necessary conditions for optimality, the Euler-Lagrange equations. So this is the preamble about this. So let us go to a simple problem of calculus of variations. So the general framework is like this. So we want to now minimize an integral functional j. Earlier it was any function f of x. X was in R or Rn, or it was generally in Euclidean space. Now I have a function j depending on the x of t, and this x of t is coming from a function space. So generally it could be a C1 function space in over AB. And then I have an integral j of this curve xt, and it may also involve its derivative x dot under the constraint xa, xb, etc. So this L from R cross Rn cross Rn to R is also the specified function, and AB is an interval in real line, and the capital A and capital B are the endpoints given. My curve, I'm assuming it to be from real line to Rn. So the A and B are starting point and terminal points are some given in Rn. So later on, we will see these endpoints need not be fixed. They can be free. Then what happens, etc. So the simple case is I'm fixing both the endpoints, and then I'm asking whether the j can be minimized over the space of smooth curves x in C1 of AB. Now this space is equipped with the usual C1 norm. So when I'm talking about the distance, it will be in the C1 distance. Okay. Now, what are the Euler-Lagrange equations? Suppose x tilde is a local minimum in C1AB for the functional j, and it's the x tilde satisfies the endpoint conditions. At the little a, it is x tilde of little a is capital A, x tilde of little b is capital B. Assume that L, Lx, Lx dot are all continuous in the neighborhood of this curve x tilde. Then the function Lx dot is continuously differentiable as the function of t. The dot represents t, and the following equation holds at x tilde. Now I have written minus d by dt of Lx dot. What it means is the partial derivative of L with respect to the third variable x dot. So L has three arguments, t, xt, and x dot t. So when I write Lx dot, L is differentiated with respect to the third argument. That is the meaning. And then the whole thing is a function of t. You can differentiate it as a function of t, that is minus d by dt plus Lxt. That L is differentiated with respect to the second argument x, and the whole thing is evaluated at x tilde. So what I mean by Lx dot of t is Lx dot evaluated at t, x tilde of t, x tilde dot of t, etc. The next one is also like that. Okay. Okay, so this is how did we arrive at, the proof is very natural, intuitively very clear. What you have to assume is x tilde, let it be the optimal or minimum that you start with. Then you have to give a slight increment, which Euler and Lagrange call variations. You give a slight, instead of x tilde, you will take x tilde plus theta h. That h will be another function, very smooth. It should not disturb the endpoint conditions, and it will be smooth enough so that you can talk about derivative. So you will reduce everything to a one variable function, theta. Now the theta, when it becomes 0, you define a new functional I of theta. Now you are in a familiar ground, that is theta. It's a function of one variable theta, and when theta is 0, it has a minimum. Then I can say I prime theta is 0. It's only in the calculation of I prime theta you have to be careful, because it will involve differential calculus in Banach spaces. So you have to carefully write down all the derivative and evaluate it at theta equal to 0, and that will give you the Euler-Lagrange equation. For example, you can find the details beautifully explained in Ivan's book in calculus. Here's a chapter on calculus of variations. There you can see the Euler-Lagrange equation derivation. Okay, so I have not included that here. Instead, I have gone to a simple example, and then I go to Brachot-Crone problem. So this is a very simple example because everything is involved will be linear and at most quadratic. So it's a quadratic minimization problem. J is x dot square plus 12tx dt. And I forgot to write what was the derivative. I forgot to write what was the differential equation. Give me a minute. I have to check my notes. I think it's x dot is t or u plus t plus u. I'll see the example. Yeah, I have got t cube. So maybe it's t square. So it's unfortunate. I have forgotten to write my, yeah.
Excuse me, is it d by dt?
It was, yeah, it is d by dt. You are right.
And there is
I
a
have
minus sign there. Yeah, minus
Yeah,
is there.
yeah,
Okay,
yeah.
no
You
problem.
are right. There is a minus sign. This is d by dt of 2x dot. That's how I am getting x double dot. So this will give me minus 2x double dot plus 12 is 0. But the constraint I have forgotten to write. I think there must be a differential equation at the background. So what was the yeah, so maybe this is enough. Yeah, these are the only constraints. X0 is 0 and x2 is 8. That's all. I had made a mistake in d by dx. This should be d by dt. So d by dt on 2x dot will give me 2x double dot plus 12t is 0. Okay. So this is the Euler-Lagrange equation applied to J. Okay.
Madam, there are a
Yeah.
couple of questions. Shall we take?
Yeah. Let's take that now.
Okay. So one question is, you have mentioned J is in C1 space. If the integral function J is in C2 space, then how can we write integral function J?
I didn't follow. Can you repeat the question?
You have mentioned J is in C1 space. If the integral function J is in C2 space, then how can we write integral function J equal to? I think when J is C2, he wants to know the
No,
formula.
C1 or C2 doesn't affect the values taken by J. J is a real valued function of all these variables integrated out in T. So ultimately, J is going to be a number. J will be, I'll take it from R T variable, which is varying in R. The L, let us look at L. So the x variable will lie from Rn and x dot is in Rn. So the L will also be a real number. It's taking real values. So in the integrand is completely a real number. I integrate it from A to B, so I'll get a number. So J is ultimately a real number. That is why I can talk about minimization or maximization. Is that okay?
Yeah. Okay. So next one is, could you help me to
So,
understand
just
why?
a minute. So to
Yeah.
continue with that, C1 or C2, here I have mentioned X is in C1 of AB, and the X is sitting as the second argument of a capital L. So that can come from very smooth curves or less smooth curves, or so here I have taken it to be C1 curves. X can also come from C2 curves. That is also possible. It's up to you to choose what space do you work in. So ultimately, when here I have said J satisfies all this. LX, LX dot, they all should be continuous in the neighborhood of this curve. The curve is lying in Rn. Okay, for AB, starting real values from AB, I get the values in Rn. So the L is a function of T, X, and X dot. So all these quantities, I want it to be continuous in the neighborhood of the curve X tilde in Rn. That is what I mentioned. Okay. Yeah, go ahead, Abhay.
Could you help me to understand why x0 equal to capital A in Rn and not a real number? Here, I think we are taking x as elements of C10A.
Okay, so there is a confusion here. I have to explain. My arc X is going from AB to Rn. So X of T is not a real number, but it's a vector in Rn. Okay, so that is why I wrote xt is sitting in Rn. Now, if xt is sitting in Rn, x dot t will also be sitting in Rn. So that is why the curve, can you think of a curve in a space curve or a plane curve? A plane curve takes the real interval AB to R2. A space curve takes the real interval AB. For each t in this AB, it will give me a value in R3. So I am taking in general Rn. So that is why the values, the images are all in Rn. That is why XA should lie in Rn. I cannot write otherwise. A and B will have to be in Rn because the values of X are all sitting in Rn. They are all n vectors. Does it make sense?
Maybe you could use a index notation like xi of t and xi dot of t, so that it looks like
It will be,
it goes from
I'll
1
get
to
it
n.
more confusing if I write X is equal to X1, X2, Xn. And then X dot will be X1 dot, X2 dot, Xn dot. This is the meaning. But
Yeah.
if I start writing, it notation will run for the whole page. So it's a compact notation for this n vector xt. Okay, so this is the notation. Once we accept this notation, I will go ahead with x. X is a vector. We have to remember. Whereas t is a scalar. Okay.
He says it's clear.
Okay. Okay. So let us
And
go forward.
there is
Yeah.
one
Any
more,
other? Yeah.
but I don't know which problem he's talking about. I will read anyway. If
Yeah.
we introduce this problem for conjugate points, how we can write sufficient conditions for optimal control problems?
Okay, I don't understand. I haven't yet come to optimal control. So let's worry about it later. And I also don't want to worry about conjugate points right now. But let's take it up when I come to optimal control. Let me continue with calculus of variations for the time being. Okay. So this is the main theorem where Euler-Lagrange equation is written, and I am trying to find the solution to this equation. So I have 2x dot plus 12t is 0 is what Euler-Lagrange equation gave. Okay, because d by dt gave me 2x dot gave me minus 2x double dot. Okay, now I have to integrate twice. I'll have two constants. How do you eliminate the constants? You see here in this case, x, I have to clarify here. It's a simple case where x is going from 0 to luckily to r. So there is no confusion. So all are real numbers here. Okay. So here I don't have to worry about vector notation, but the earlier slide I had x as a vector, n vector. Okay. So after integrating, I'll get two constants and I eliminated. So the constants are a and b. So I have got tq plus at plus b. So now you put x0 is 0. So that will kill b. So b will be 0. Then you calculate x2 equal to 8. That will give me what is a. And I finally find a is also 0. I get the solution to be xt equal to tq. So what we tried to do is we had an integral to minimize under some constraints. It was very similar to Brachistochrone problem, but in a slightly simpler one. So now that we understand how to use the Euler-Lagrange equations, let us go to our Brachistochrone problem. And here we first have to formulate the problem. What is the path taken by a particle sliding freely from point A to point B, freely under gravity in shortest time? There is no friction. Okay. So for simplicity, you can take A to be 0. So let's take A to be 0, y1 and B to be some b, y2. So will it be a straight line or will it be like this? We don't know what path it will take. So it has to slide from 0, y1 to b, y2. This is b, I erase this and write it clearly. This is b, y2. Okay. So I have to first find the integral function, which will give you the time taken to slide from one point to another. So as before, I have to write the time as the length divided by velocity. So I'll have to find expression for all this. That will give me the expression for final J to be optimized. So for that, first we will find out what is the length of the curve. So I'm taking the path to be xt comma u of xt. We don't know what curve it will take. It may not be a straight line. So I have taken it to be some unknown function u of xt. And so then LT will be 0 to xt of square root of 1 plus u prime x square dx. This is the usual formula you will find for arc length. Thus, the velocity of the particle will be derivative of L with respect to S evaluated at t. So that will give me the derivative of x and the integrand evaluated at xt. And so I have written the velocity. But I have to calculate the velocity. Also, we can compute from the conservation of energy. There is no extra energy given to the system. So the energy, total energy at 0 will be the total energy at t. And the total energy, the initial velocity is 0. And that will give me the velocity. The velocity is given by 2g y1 minus u of xt. So I have some expression for this. And here also I have some expression for velocity. So I'll try to use these two and combine and write x prime t as this by this. Why I'm doing all this? Because I want to know what is t prime of x. T prime of x, then I integrate it, I'll get the total time. This is another way of finding out. There are several ways of arriving at this. So I have taken this particular route. So x prime t I have written finally this way. Assuming the path t to xt is invertible, I'll get t prime x to be the inverse of this. And then the integrating the t prime x from 0 to b, I get the total time to slide from a to b will be the integral of these function. Now this is to be minimized for over all the C1 paths U, which is connecting from Y1 to Y2. So this is the problem. We have formulated the Brachistochrone problem to the model problem. I have an integral functional and I have to find out what is the minimum of this. So you could simplify. So I forget. We can make y1 to be 0, and finally I can make a simple reduction to L equal to square root of 1 plus u prime square by ux. Now, what is the Euler-Lagrange equation for this problem? I have integral of, I have integral from 0 to, I forget, 0 to b, I think. Yeah, 0 to b. Square root of 1 plus u prime square by square root of u dx. This is my j and this is the L. Integrand is the L. So what is the Euler-Lagrange equation in this case? It will be minus d by dt of x, the Lx dot t. Now, I have, instead of x dot, it will be u dot. So I have to be careful when I am writing. So the u dot, when I apply u, it will become u double dot or u double prime at xt into u of xt, because the square root will give me that is equal to half into 1 plus u prime square. So finally it reduces to this. But this is also not easy to solve directly. So you have to multiply by something, bring it to an amenable form, and then use the sine theta, cosine theta substitution. And it can be solved after some steps. It will lead to the parametric form of the cycloid, which is x theta is half k square into theta minus sine theta, and y theta is half k square into 1 minus cos theta. So this was one way of arriving at the solution, but there were several, as I told you, there were several other people who came up with different approaches, but they all led to finally the cycloid. Okay. Now I said the endpoints were fixed. So what if the endpoints are not fixed? What happens? Can you solve still? So in that is also possible. There are free endpoints, both endpoints free. So there are several possibilities. I have taken up only one of the possibilities. Suppose x tilde is a local minimum in C1AB, in the space C1AB for the functional j. Then the following equation holds at x tilde. Again, I get the same Euler-Lagrange equation, but in addition, if the final state is free, because if the final state is constrained, I get conditions at the two endpoints A and B for x tilde, which is coming from the constraint. Now I have removed one constraint at the endpoint B, so the final state is free. Then there is a transversality condition which you have to add. That will be the L partially differentiated with respect to the argument x dot evaluated at B should be 0. So this extra condition will help you to settle the endpoint, what is missing. So to understand how to use this, I have added one simple example. Let's see if I can finish that example and then consider the following same minimization problem I have taken. X dot square plus 12tx dt 0 to t, but now only x0 is 0. So you remember it's the same problem I did before. X dot square plus 12 tx dt. Initial condition x0 is 0. I had final state as 8. That was fixed. Suppose I drop the final state. So the final state is free. Now there is a theorem which tells you have to add a transversality condition. So our aim now is to understand what is the transversality condition in this example. Let us see if we can write it down. So x0 is 0. Now d by dx. So this is the Euler-Lagrange equation which I got earlier also. And that will give me x double dot. And so that integrating twice, I will get the same equation with a and b. But how do I solve the for two unknown constant? One is easy, x0 is 0 will give you, b is 0. But a is floating, I have to solve for a. For that, the transversality condition at the final point, I have to get 2x. So the derivative of L with respect to x dot evaluated at 2. What does that give you? That will give you 2 times x dot evaluated at 2 must be 0. So I have a x. So I calculate x dot t. X dot t will give me 3t square minus 12. Sorry, 3t square plus a. And 3t square plus a, I evaluate it at 2 and I put it to 0 and then I get the calculation from here. So that will settle for a. A can be found out using the transversality condition at the free endpoint. Now who is floating around? B. The B can be killed by using the initial condition because the initial point is fixed, x0 is 0. So the minimizer is xt is equal to t cube minus 12t. So this is one way we can use the transversality condition. Now there are many, if both endpoints free, one, etc. So that is, it will add more and more transversality condition or complementary conditions, they call it. Now let me go to optimal control problems. In many practical problems, a differential equation describes a steady state or evolution of the system. Often this problem involves some control parameters also. Our aim is to find the best control which maximize a certain payoff criterion or cost functional. So the major questions are, does optimal control exist and how do we characterize it and how do we build an optimal control? Most of the time it has to be done by computers, because by hand you can solve the ODE only in very few cases. So in the simple example, we can solve. Otherwise, we'll have to take recourse to the numerical computations. Okay. Now a little bit of comparison with the calculus of variations. So optimal control theory also treats problems very similar to calculus of variations, and but it's taken from a dynamic viewpoint. In the sense, earlier I did minimization of functionals, where with the endpoints fixed, etc. But the constraints did not involve x dot. Now, what if the constraint involves x dot? That's what it means, dynamic viewpoint. So the constraint is going to be a differential equation. So Pontryagin and his students in around 1950 took up the study of these kind of problems, and they derived optimality conditions, now known as Pontryagin maximum principle. Now, Richard Bellman and his group same time derived dynamic programming principle using value function. So let us see some glimpse of these two. Minimization or maximization. Some later on I have taken for Bellman, I have taken maximization. So I can say optimize. J is 0 to t L of t x t of xt, x dot t, you can denote it by ut, the control, dt, such that x dot t is ft, evolves, this xt evolves according to the dynamics F. And there is a control parameter, control function, which is U. Now, this almost everywhere, I have abbreviated as AE because we can allow a weak solutions also here. Otherwise, you forget for everywhere, we can also put T in 0, 1. Now, there can be general boundary conditions. Beta of x0, xt is 0. Typically, you can put x0 is 0, xt is 0, or a mixture of x0 plus xt, a linear combination, or a linear, some kind of other conditions also. Now, there can be control constraints also. This control UT may be constrained to lie in some set U in some space. It may live in Rm or in another space. So, or it may be a real number. We don't know, depending on the problem. So this is the basic problem. You see, it looks very similar to calculus of variation, but still it's because it's constrained by a differential equation. So it is slightly different in that approach. Okay, why this kind of problems came up? The moon landing problem is a typical example which everyone will give you. So the basic question in space dynamics is you are in a spacecraft and you have to land on the lunar surface without banging on it. That is, you have to land softly, or your velocity must be 0 when you land on the lunar surface. And you also want to use minimum amount of fuel. So how do we do this? So this was one of the motivating examples at that time. The system can be modeled by Newton's equations. So V dot T, the velocity is minus G plus alpha T by mt. What is alpha? Is the thrust. Thrust is what is the control we give. And mt is the mass of the spacecraft. Okay. Now, what is the velocity? H dot T is equal to the velocity. The ht is the height from the lunar surface, or distance from the lunar surface. H dot is the velocity. M dot, the rate at which the mass is decreasing, is proportional to the thrust that we are giving. It's negatively proportional because if we give more thrust, the mass will decrease faster. So I have put a minus sign. So this is now already 3 variables, V, H, M, but luckily they're all ODEs, and the dynamics is given by the right-hand side. Now, what do we have to do? We have to minimize which functional, let us see. The problem is to minimize the fuel or maximize the remaining amount when it lands. So minimizing the fuel is equivalent to maximizing the mass, because the mass is causing the fuel is adding to the mass when it lands. Okay. So we define J of alpha dot. The alpha is the control, the thrust that we are giving, which is equal to M of capital T. That is the mass remaining at capital T when it lands. T is the first time when the velocity is 0. That is what is corresponding to soft landing. Soft landing means the spacecraft has velocity 0. So when Vt is 0, that is it lands on the surface smoothly, softly. Then the problem is to maximize J of alpha dot, because we want to minimize the fuel. The fuel will be lost less and then the mass will be more. So we are going to maximize J of alpha dot. But what are the constraints? Constraints are ht must be greater than or equal to 0. The height is always non-negative. Mass is always non-negative, and you can't give infinite thrust. So the thrust must be bounded. So I can typically assume it's bounded between 0 and 1. Okay. So so let us put it in a mathematical framework. This is the motivating example. So a general problem will be to minimize or maximize 0 to t L of t xt ut dt plus g of xt subject to the constraints dxt by dt is equal to the dynamics is given by f of t xt ut. Ut is the control. And with some kind of boundary and initial conditions, beta of x0 xt is 0, gamma of x0 xt is 0 in Rd. There can be several conditions. We don't know. That's why they have put it in general. So control ut is in a non-empty closed convex subset of U. Add stands for admissible control space, contained in some m-dimensional Euclidean space. J is the cost functional, L is called the running cost, and G is called the terminal cost. So this is the setup for optimal control problems. And then we will see here also, how do we write down the Lagrange multiplier and how do we write down the kind of Euler-Lagrange formula here also, and can we use it?